Lesson 6-4, solving special systems. These are ones that don't have a typical solution, like the problems you've done in 612 and 3. You're going to need your Know-It Notes, pages 84 and 85. You should not need any extra paper. There should be plenty of space there on page 84 for the examples that we do. Okay, there's some vocabulary and chart copying and things to do here, so let's get started with it. In lessons, really 6, 1, 2, and 3, we learned that when lines intersect at a point, we could find that there's exactly one solution to the system. Those kinds of systems are called consistent systems. So on page 84, fill in the vocabulary word there, the vocabulary phrase with the definition, systems with at least one solution for consistent systems. I know it's not the typical meaning of consistent, but that's what it means in this case. Okay. Consistent systems can either be independent or dependent, just like we use for the variables, although they don't mean the same thing here, unfortunately. I wish they would use different words, but this is what the words are, so we're going to go with it. Independent system has exactly one solution. So everything you've done so far, right, in lessons 6-1, 6-2, and 6-3 have been consistent, independent systems. Okay, they have exactly one solution. They are two intersecting lines. A dependent system, it's still consistent, but it's dependent, has infinitely many solutions. The graph of a dependent system is two coincident lines, and really that just means it's the same lines graphed on top of each other. Okay, it's kind of like all real numbers. And there's an infinite number of solutions from the same line. That's a dependent system. Think about one line depends on the other. Okay. Inconsistent systems, this is the last vocabulary term there on page 84, don't worry yet about the chart on 85, is a system that has no solution. And where those are going to come from, parallel lines are inconsistent, right? They're never going to cross, so they can't have a solution, and we call those ones inconsistent. Now focusing on the chart on page 85, I'm going to bring up the same chart that's in your textbook and it's on that page, just with nothing filled in. So go ahead and pause the video and copy the examples in. So you've got room for the description, how many solutions, and what it looks like. Okay. When you're ready, come back. Now that you're back, we're going to move on. And somewhere there on page 84, or squish it down there at the bottom, page 85. We're not actually really going to use those other boxes on page 85 because they really are the same thing as the chart above it. I'm not sure why they give you two places to do the same thing. I want you to write down the two ways that you can figure out if a system is inconsistent. One way, you can put both equations into slope-intercept form. Really should say put both equations into slope-intercept form and compare the slopes and see what happens, right? If they have the same slope and different y-intercepts, then they have to be parallel. Option 2, solve the system algebraically by substitution or elimination. And if you get something false at the end, then it's inconsistent. So if you end up with like 5 equals 3, then that means that there's no solution. It's an inconsistent system and the lines are parallel. Let's look at a few examples here. On page 84, we've got plenty of room for examples. And right now we're just looking at, is this a consistent or inconsistent system? So is there a solution, or is there, or lots of solutions, or is there no solution? The equation, one of them is already in slope-intercept form. And so let's go ahead and try method 1 here, where it asks me to compare slopes and y-intercepts. So I'm going to solve the second equation for y by adding x to both sides. And so now I have y equals x plus 3. The first equation slope is 1, and the y-intercept is -4. The second equation has a slope of 1 and a y-intercept of +3. So they go through different places on the y-axis, but they have the same slope. that means these lines are parallel. And since the lines are parallel, that means there is no solution. So it is an inconsistent system. If I ask for how many solutions there were, you would say none. But if I ask you whether it's consistent or inconsistent, then you would say it is an inconsistent system. Let's look at one more like this. I know this vocabulary is new and kind of tricky, so just keep checking your notes. Think about what you wrote down so you can match it. Okay. Now this is actually the same problem, okay? But I want to show you how you could solve it algebraically, because especially this is just presented as one of 10 problems to solve. You might not think to yourself, oh, those look like they might be parallel lines. You're probably just going to think, all right, I'm going to solve it. One of them's already solved for y, so let's just go ahead and substitute x minus 4 in for y, and we get negative x plus x minus 4 equals 3. And now when I go to combine my x's, they all disappear. So I have negative 4 equals 3. Well, negative 4 doesn't equal 3, so that tells you there's no solution, and still you would say it's inconsistent. So remember, this is the same exact problem, just done a different way. And I would say that way, the algebraic way, is probably more common because we are usually doing these as part of a bigger set of problems where we're not expecting there to be no solution. Now we have a different problem. So determine whether this system is consistent or inconsistent. Use either method. Go ahead and pause the video, give it a try, either doing it by solving for y in both equations or by using algebra. Now that you're back, I'm just going to use the algebraic method because, like I said, I think it's more common. So I'm going to solve the second equation. Oh, I don't even have to solve the second equation. Let's just do it this way. Let's just substitute negative 2x plus 5 in for y, and we get 2x plus negative 2x plus 5 equals 1. And those cancel out. 5 equals 1. Not today. So no solution. So this system is inconsistent. You don't need to write this down, just read it along with me here. If two linear equations in a system have the same graph, the graphs are called coincident lines. Right? And that means there are infinitely many solutions of the system because every point along the line represents a solution of both equations. So if you imagine that this is two lines on top of each other, right? Every place along this line, every single point along that line is a solution because it's part of both lines at the same time. Kind of like all real numbers. So you can once again either compare the slopes and the y-intercepts by solving both equations for y. If they're the same exact equation, then they're the same exact equation. That makes it a consistent, dependent system. Okay. Otherwise, you can use algebra. I'm likely to use algebra because I'm not thinking, oh, right, it might not have a solution. I'm thinking, oh, I'm going to solve it. I'm going to keep using substitution. Actually, no. Let's use, well, I'm going to use substitution, but maybe a little bit different. I'm going to solve this one for y. So I get 3x plus 2 equals y. Oh, well, I was going to do substitution, but now I can already see that I have the same thing, 3x plus 2 and 3x plus 2. So there's no reason to keep going. If I did keep going, for those of you who don't pay that much attention to what's on both sides of the equal sign all the time, you get, oh, 3x plus 2 equals 3x plus 2, right? And when you subtract 3x from both sides, you're going to end up, right, either with eventually 0 equals 0 or 2 equals 2, right? Something like that. And that's true. Okay? But it's not just all real numbers. It's all real, correct sets that would fit on that line. So you don't really give an exact solution. You would just say that this system is, you can say that there's infinite solutions. Not all real numbers, because it's not every single number. It has to be a special pair of numbers. And so infinite solutions, that does, by the way, make it consistent and dependent. If I want all of those things, I'll be very specific in the question. you would just say there are infinite solutions for this problem. Try this one, see what happens. Pause it and come back in a moment. Okay, now that you're back, I think I'll use substitution this time. Might not be your choice, but that's okay. You can do it the other way. And so I'm going to plug in x minus 3 for y. Now I do have to be careful here because both the x and the 3 are subtracted here. So might want to zip, zap, and distribute because I get x plus negative 1x, and then I have negative 1 times negative 3 is plus 3 minus 3 equals 0. And now all this stuff cancels out. X plus negative 1x and 3 minus 3. So I end up again with 0 equals 0. So there are infinite solutions. So it is a consistent, dependent system. By the way, that's an infinity sign, in case you didn't know that. Infinite solutions. I think we've got a word problem. That might be it. Jared and David started a savings account in January. If the pattern of savings in the table continues, when will the account in Jared's account equal the amount in David's account? All right, so David starts at 40, and he increases 5 every month. Right? So if we were going to write an equation for his money, his output is 40 plus 5x, because every month he gets 5 more dollars. Right? This is month 0. February's month 1. Right? Month 2, etc. And Jared, he started at $25, and he's also adding $5 per month. Okay. Well, now when I look at my two equations, I notice that they have the same slope, and they have different y-intercepts. So those two lines are parallel. And if those lines are parallel, they are never going to intersect. So the answer to when will the account in Jared's account equal the amount in David's account is never. It can never equal it, right? Because they're increasing by the same amount every month, and David started out ahead. So unless Jared saves more per month, he is never going to catch up, right? You got to have your logical thinking brain on. Tomorrow we'll talk more about these, a little bit more about maybe some good methods for memorizing those vocabulary terms. But the nice thing about this is usually the math part, the number crunching, the algebra crunching is a lot easier. That's it for today.